Okay, let me see. Can I? Is that an option? No, but that's okay. There it is. Okay. All right. Let's try this one more time. Sorry, it's people just keep trickling in and they keep catching my attention, so I'll go ahead and give them credit. Okay. So I will check the attendance again around 1:15, or at least I'll attempt to. Let me see as far as announcements go. Hope everyone enjoyed your weekend, right? So we are at the top of week 5, right? So let me see. Our exam 1 was due this last night at midnight, right? So, but as with so you should have noticed several things with it, but you'll discover that as you take it. The exam had the same properties: unlimited attempts. The system is set to take your highest score. Also, just like all of our assignments on Pearson, you can work on any assignment past the due date with only a 10% late penalty. So if you made less than a 90 and you want to improve your score, you can always go back all the way up until the very, very last day of the semester. You can go back and improve any score. All right, I just went on and set that. That's just a simple thing. Instead of students requesting extensions, I already built it into the structure. Let me see. So, let me see some other suggestions. So it is a good idea. I do encourage you all to work together. I do encourage you all to seek out the tutors, and you can work on these assignments with the tutors, right? You're not in this alone. And again, the idea is that my intent is to use class time as like a Q&A or office hours or study session. I just fill it with like lecture and homeworks just to come with some material. But if you guys want to talk about something else, we can. There was something else I wanted to say. Another update is that, so on basically all the stuff that you guys have seen me writing, I went on and updated the folder. So if you go to like our Blackboard page, let me see if I have it. I'll open up Blackboard. Let's just do a new, come on. It's kind of slowing down on me. So let me see. I'm just opening up our page. So if I go to Blackboard, and if I open up our Blackboard page, which is College Algebra 2, okay, open up our main folder. And then, so if we go down to where it says daily lecture notes, box link, if you click on that link, I'm gonna go ahead and click on it. For me, it's gonna, it opens up box and it takes us right here. So if you go to folder number 1, it says notes and then updated College Algebra 2. So anything with anything that you see me write on the screen, basically at the end of each session, I'll drop it into this folder, all right? So, you can access anything that I've been writing. Any PDF will be located there. Okay, again, and I'll check for the stragglers as far as attendance goes in about 10 minutes. And so let's just go ahead and hop into the material for today. I think the main things have been shared. So yeah, let's go ahead and. So today, I think we are continuing chapter 3 with section 3.2 log functions, right? Let's see if there's anything else. Yeah. So 3.2 is over logarithmic functions, and a few objectives are the following. We'd like to define logarithmic functions, evaluate logarithms, find the domains of logarithmic functions, graph logarithmic functions, and use logarithms to solve exponential equations, right? Okay. And as usual, if anything is not clear, feel free to either unmute yourself to catch my attention or type in the chat. And also, this is a remote asynchronous, so If you're in my Zoom call right now, that means you've already gotten your attendance credit for the day and you're not obligated to stay. Again, I'm just making myself available, you know, and however you get the information is fine with me. If you can get it from me, that's great. If you need to work with somebody else, go ahead.
Excuse me, my name's Kadar. I just had a quick question regarding the exams. So I took the exam and I'd gotten a couple of points deducted as a result of like a syntax issue with like Pearson. So like, for example, I believe one of the answers was -8/7 for the question that I answered, and I put it in as -8, like with the 8 -/7, which is the same answer. It's just the negative is in a different location.
Let's talk about that like when we have about 15 minutes left, like about somewhere between 1:40 and 1:45 towards the end of class.
Okay. All right, thank you.
Mm-hmm. Okay. Yeah, we can definitely look at that. And so my goal is to like, okay, for today, we'll go through as much of the lecture as we can. But again, this lecture is already available, right? So the recording for this is already there. And then on Wednesday, we'll go through as many homework questions. And we'll take some time at the end to kind of clear up that item. Definition of a log function. So for here, let's go with this. I like this. So for x strictly positive, a strictly positive, and a not equal to 1, we say y equals a log base a of x, if and only if x equals a to the power of y, right? So you'll see momentarily how we can correlate this log form to this exponential form, right? When you do it a certain way, these mean the same thing. The function f of x equals log base a of x is called the logarithmic function with base a, right? The logarithmic function is the inverse function of the exponential function. So I think last time we did exponentials. So write each exponential in logarithmic form. Okay, so let me go back. So here, the connection, like how to convert from log form to exponential form, basically when you're going from one form to the other, all you're doing is swinging the base, right? So for instance, in log form, can anybody tell me the base over here in log form? What's the base?
Y equals log ax.
So what's the base, right? What's the base?
Is it the a and the x?
Yeah, just the a, right? So in log form, our base is a, right? To write this in exponential form, we swing the base over, and now the base of the log now becomes the base of our exponential, and we just drop the log, right? So then you'll see it right here. It's going to be x equals a to the power of y, right? And then the reverse is the same. To go from exponential to log, you swing the base. So the base of the exponential is a, it becomes the base of the log. So when you do it that way, these two are the exact same. It says two different ways of saying the same thing. Okay. So then,
hello?
Yes.
Oh, I'm sorry. I mean to cut you off.
Good.
I have a question about like this first statement. It says for x is greater than 0, a is greater than 0, and a does not equal 1. Can you explain that for me, please?
So that's just the general form of the log, right? The domain for log, for instance, log is not defined when x is either 0 or negative. So for log function, it'll make more sense when you look at the graph. Like the general shape of the graph of log, if that's the xy plane, it comes up and then it goes off like this. So that domain is strictly greater than 0, strictly to the right-hand side of the y-axis. So that's where this guy is coming from. The base has to, and then we're not going to talk about where this base is like negative or equal to 1. Let me see. If the base is 1, then it no longer behaves like a log. It's like a constant function, right? So these are two stipulations for the base in order for us to for these to behave proper, right? And you don't have to read too much into this. It'll start to come out naturally. The main thing here is that our domain is 0 to infinity, the open interval 0 to infinity. And then just whenever you're working with the bases, they have to be strictly positive and not equal to 1. Let's work a few examples, and I feel like that'll become a lot more clear after the examples. Write each exponential equation in log form, right? So we want to convert these exponential forms to log form. So what we literally just said, to go from exponential to log, we swing the base, right? So the base of the exponent on the left is the 4. So when we swing it, the 4 is going to become the base of the log. So then we're going to get 3 equals log base 4 of 64. And that's going to be the exponential form of this log. Okay. Let's try the next one. So the base in this one is going to be the 1/2. So that guy is going to swing over and become the base of our log. So then when we swing the 1/2, we'll get 4 equals log base 1/2 of 1/16. Okay. And if for part C, we do the same thing, swing the base. So the base A becomes the base of the log on the other side. And we'll get -2 equals log base A of 7. Okay. So we got log base 4 is 64 equals 3. Now I'll show you a little bit later on how we can verify these in the calculator. There's a technique that's coming up. Well, we can at least verify the first 2 in the calculator. Okay. Are we missing one? No. All right. Is equivalent to log base 4 is 64 equals 3. And you see the other ones here. Okay, so that was going from exponential form to log form. So then now let's go from log form to exponential form. So again, when rewriting exponential to log or log to exponential, all you have to do is swing the base. So the base here is the 3. All right. So we swing the base of 3 and it's going to become our base for our exponent. This is going to become the base and this is going to become the base. Okay. So if we account for those for part A, that's going to give us 243 equals 3 to the power of 5. See how 3 is the base of our exponent? For part B, this is going to be the same as, is that 5? What do I feel like that should be? Anyway, it looks so weird. I feel like something's missing from there. But 5 equals 2 to the power of x, right? We just did the same thing, just changed out the, just kept whatever was there. And if for part C, if the base swings, you'll get n equals a to the power of x. Okay. 3 to the power of 5. Okay, you see it here. 3 to the power of 5, 2 to the power of x, a to the power of x. Okay, so in these first couple of examples, we saw how to convert from exponentials to log and vice versa. Let's dig a little bit deeper. Hey, thanks. Thank you. Come here. Come on. Thank you. I know. You hear something, you got to say something, but this just isn't the time. Okay. Find the value of each of the following logs, right? Okay, so let's just start with the first one. I actually think I might need some space. Let me give myself some space. All right, so this first one, we got log base 5 of 25. Now, it says to find the value. So basically, we're just evaluating. Let me think about it. So my favorite way to go about these, I'm not going to say the shortcut just yet, but I like to set it equal to y and then just basically do what we were just doing where we rewrite these as exponential. So swing the base. Okay. So then if we rewrite this as an exponential, now the purple is what I introduced, and then the blue is the technique that we were just doing. All right. So now if we rewrite this log as an exponential, we're going to have 25 equals 5 to the power of y. I'm just going to reverse the order. If the left equals the right, you could switch them around. That means the right equals the left. And also, you got 5 to what power equals 25. I'm going to rewrite the 25 to have the same base, right? So 5 to the power of y equals 25 is what? 5 squared. So then all you have to do is match up your exponents. So then from there, it should be clear y equals 2. okay? Now, there is a way to evaluate this quickly in your calculator. I'm just trying to save it for, because that should be in the notes and it's coming up. So we're gonna wait. Also, so I wanna say that a student version of all the notes should be available. So you can actually pull these notes in advance and try this stuff. And then at the end of class today, I'm gonna load the notes that I'm working on. These are the instructor notes, so they have all the missing details that are not in the student version. Log base 2 of 16. Log base 2 of 16, right? So again, to evaluate this, first I'm going to set it equal to y and swing my base, okay? So then I'm gonna have 2 to the y equals 16. I'm gonna write it like this, 2 to the y equals 16, okay? So then I want to write these with the same base. So I'm gonna have 2 to the y equals, I think that's what? 3, 4, 2 to the power of 4. All right. Okay, I think that's fine. So then y equals 4. Copy. And just stop me if anything isn't clear, or I know I might be talking a little bit fast. Let's see. Let's work on part C. Oh, okay. Seems like it's quiet now. You good? Oh, now you got your. What you gonna do? Come on, make a decision. Are you gonna sit down or you gonna hop down? Thank you. We did hop down. If we didn't hop down, I was gonna push you down. I'm not really gonna push it down, but okay. So we got log base 1/3. Okay, is one. I think we're okay. Of 9. Okay, right. So if we work this one the same way we did the previous, I'm going to set it equal to y and swing my base. I'm rewriting the log as an exponential. Okay, so this is going to give me 1/3 to the power of y equals 9. Okay, so that 1/3, I think I'm a fan of rewriting that as a negative exponent. 1/3 is the same as 3 to the power of -1, right? So I'm going to write it like this: 3 to the -1 to the power of y. And then maybe we can get that 9 to a base of 3. So that's going to be 9 is what? 3 squared. And then one more simplification, I'm going to say 3 to the power. So when we say a power to another power, like Baby's Kids, we do not die, we multiply, right? I know that's totally outdated, but if you have not seen Baby's Kids, check it out. It's an old animated movie. I don't know if it's still funny today, but I know it was funny when I was younger. It might be, it should be outdated by now, but it's just a fun movie. It's just an old fun movie. And then 3 squared, right? So now we've got two exponentials of the same base. We just equate the exponents. So that means -y equals 2. So then y ultimately equals -2. So once you get the exponents of the same base, then you can just equate the exponents. Okay. All right, A, B, C, D. Log of 7, base 7, okay? A, B, C, so then D, oops, right here, D. We got log, log base 7 of 7. Again, I'm gonna just set it equal to y and swing my base. So then if I rewrite it, I'm gonna have 7 to the power of y equals 7. I'm just gonna, this is implied, there's a power of 1. So then from there, you should be able to see y equals 1. Okay, see the time. Let me try to finish this one out, and then I'll check for any stragglers. E, come on. Log base 6 of 1. Okay, I'm gonna set it equal to y, swing my base, and let's see what happens. So we're gonna have 6 to the power of y equals 1. How can we get these to both be base 6? How can we get them to the same base? So then 6 to the power of y equals 6 to the, anybody know that power? 6 to what power will give you 1? Anybody know that one? Going once, going twice. 0, right? 6 to the power of 0 equals 1. So then y equals 0. Okay, paste. Let's keep it moving. A, B, C, D, E, F. Let's give a little bit of space. And that's good. Okay, so F, log base 4 of a half. Log base 4 of 1/2. We have log base 4 of 1/2. Hang on, this is like working me. That's good there. Okay. So we're gonna set this equal to y. Man, I'm being totally OCD today. I don't know why. Swing the base. Basically, in all these examples, we did the same thing with the purple and blue, purple and blue. It's the same thing and just catching the changes. Okay, so let's keep going. So we're gonna have 4 to the power of y equals 1/2. Okay, and I'm just gonna kind of do it just for the sake of time. So we got a 4, one is base 4 and one of them is 1/2. If we want to get them both to a similar base, I'm thinking we can get them both to a base of 2, right? Because 4 is going to be what, 2 squared? So we're going to have 2 squared to the power of y. 1/2 is the same as 2 to the power of -1. Let's clean it up just a little bit. And then, you know, a power raised to another power, we multiply. So this is equal to 2 to the power of 2y equals 2 to the power of -1. So then this means that 2y equals -1. So then y equals a -1/2. Okay. So, you know, we evaluated all of these by hand. There is a shortcut for these. It should be coming up. I'm just trying to save it. Okay. So 2, 4, -2, 1, 0, -1/2. Let's see. 2, 4, -2, 1, 0, -1/2. Okay. And it looks like they were pretty similar to what we were doing. So, okay. All right. So look at this. Let's try this one. We're asked to solve each equation, right? So again, it's given to us in log form. We can convert these to exponential form. Let me give myself some more space again. See, like it's okay. So like what you see me doing, this is what I was doing in grad school. Like, I don't know why, but I really enjoy taking notes on this device. This is basically an iPad with the Apple Pencil, and it's so smooth. Like, I know it's a shameless like marketing for them, you know, making them more money. But I mean, it's been serving me for years now. It's been at least what, 5 years? No, a decade. Yeah, it's been about a decade. And like it's been, but it works really nice. Like if you have unlimited paper, as long as you have power, you know, you can charge it, you know, everything. And the pen charges in like a 15-second charges it for like 30 minutes. All right. So if you're on the go and you just didn't charge your pen, you plug it in for like 15 seconds, you get 30 minutes of juice. I'm like, man. So like if you want a project, like I don't know if any of you guys are like engineers or anything like that, but that's the next, like that's one of those things that we need is like really fast charging. Like how can you make a battery that charges like in an instant? You know, like can it charge off of sunlight in an instant? Can it charge off of like what can you get it to charge off of? And how quickly can you get it to charge? And how long can you get it to hold the charge? Right? Take it to the next level. Like, and that's an old concept. That's something that's like 5 or some amount of time ago. I saw people working on that. I don't, you know, I haven't really seen it brought to life. Another thing, if you want a project, especially if you do cosplay. So over the holiday weekend, I did go to Dragon Con, like a parade. I wish I didn't even think about it. I would have told y'all to show up, but it's free every year. You just show up on Peachtree Street at like 10 in the morning and it's free. And you get all these people in cosplay, but like one time I went, this guy was walking in like a a movie quality Iron Man suit. I was like, and I was chatting with this guy. He was like, yeah, most of those are 3D printed. I was like, oh, that would be a fun project. 3D print an Iron Man suit. And then he was like, you know, you polish it and finish it with like car paint and stuff like that to make it really look good. I was like, man, that would be so much fun. Just walking around with a 3D printed, you know, movie quality Iron Man suit. So that's just another project. Just throwing that out there. So between using this device, fast recharging batteries, 3D printing, whatever you want, from houses, you know, Iron Man suits to whatever, you know, it's so many things that we can like be working on. Some of it could be for fun, but then it can turn into like true projects for like things like I've seen where they've built like they've 3D printed buildings like houses for like people in like a disaster area and they need like temporary housing. You know, it's so many things that we could be working on. Clean energy, all sorts of things. Don't even get me started. That's what I'm really trying to build so that I can like start working on these projects. I got a ton of ideas. They just keep coming. Anyway, getting back on track. Let's see. And again, we have a recording of all of these examples, so you should be able to pull those. And you know, whatever we don't do together should already be there. So let's solve this equation. Let's start with the first one. Oh, I'll give us, let me see, got some paper, okay. Let me, do I need that? We're gonna take it from like here to here is good. I want to take it and drop it right here. Boom, crop. Come on. Crop. Done. Okay. I'm kind of using this as a reference. I guess it can stay that size, so I'm just going to rewrite it anyway. Okay. So then for part A, we're working log base 5 of x equals -3. All right. Give me just a moment. Okay. Where'd it go? There we go. Okay. Cool. So log base 5 of x equals -3. So let's try the same technique that we were just doing. We're going to rewrite these logs as exponentials. Okay, and let's see what happens. So then when we swing the base of the log and it becomes the base of the exponent, we'll get x equals 5 to the power of -3. Okay. Okay, so then that's going to be equal to, I'm going to rewrite this as 5 to the 3. Here, let's just, the negative exponent means it goes to the denominator, 1 over 5 to the power of 3. So then that's 1 over 125. Okay, let's try B. So we have log base 3 of 1 over 27 equals y. Okay, let's do the same thing. We swing the base. So then I'm going to write it in the following way. 3 to the power of y equals 1 over 27. We want to try to get both of these to base 3. So then we have 3 to the power of y equals, now 27 is what? 3 to the power of 3. So this is going to be 3 to the power of -3. So then it should be that y equals -3. And when you get the shortcut, then you'll see a quick way to check these to confirm that these are correct. I'm just saving it for right now. Okay, thank you. Log base z of 1,000 equals 3. Log base z of 1,000 equals 3. Okay. There should be enough space. Okay. So same thing, let's swing the base. So then we're gonna have z to the power of 3. If it's 1,000, I think that's 10 to the power of 3. So then we can say, you can like cube root both sides. Long story short, z equals 10. Okay. And then for d, okay, let me write it here. Log base 2 of x squared minus 6x plus 10 equals 1. And I'm gonna just, actually, I'm not gonna cut it because it's gonna mess up my copy. Oh no, oh no. Shiesta. Do I have to redo that? Let's see, undo. Can I just, come on. Okay, I think I can separate those. It's like this. Okay. Sorry. Okay, so I go like this. Okay, I got it. Sorry, it's just been a little bit temperamental. I'm gonna go like this, and then I'm gonna just click on this. That's fine. I'll get that out of there. It's just the L and the O like this. Okay. Boy, that was like hard for like no reason. Come on. So then this is here. I think that was like some kind of update because it didn't used to do that before. But anyway, let me check one more time. Log base 2 of x squared minus 6x plus 10 equals 1. Okay. Right, so let's do the same thing where we rewrite the log as an exponential. So then on the left-hand side, it looks like we have this x squared minus 6x plus 10 equals 2 to the power of 1, which is just 2. So then it looks like we're solving a trinomial. So let's set it to 0. I'm gonna subtract 2 on both sides. We get what, plus 8 equals 0. So then we want to see, can we factor into some form like this, x and x? Two numbers that multiply to give us positive 8 and add to give us negative 6. 4 and 2, negative 4, negative 2. Okay. If you set each of these to 0 and solve, you get x equals 2 and 4. Okay. I really want to check these in the calculator, but I'm trying to save that for when it pops up. Okay. So hopefully that was okay. We got a solid 10 minutes. So we got 1 over 125, negative 3, 10, 2, and 4. 1 over 125, negative 3, 10, 2, or 4. Okay. Let me check Zoom really quickly, just see how you guys are doing there. The chat looks clear. Oh, we got some stragglers. Okay, let's get these guys. Let's see. I'm gonna log back into this. I know it's already there, but let's see. G. Okay, here's this student. That's one. This student. I don't know who Quincy is. I'm gonna harass him a little bit. Quincy, I don't have your last name. What's your last name, Mr. Quincy? So I don't see you.
Sorry, my Zoom was acting weird. It's in Gordon.
Gordon, I found it. Okay. Thank you so much. Okay. Let's go back to the screen. Start the broadcast. Okay. All right, yeah, let's keep going. All right, so we did that example. Let's try another one. So we have like some more terminology. We have the domain of the log function, right? I wish the image will pop up because I feel like this is a lot easier to see with the image. The domain, okay, so just as a recap, as a refresher, the exponential function kind of starts off flat and then grows like this. That's exponential. The log function, if you rotate that about the diagonal y equals x, you're going to come up vertical and then go off to the side like this. So this is the general shape of a log function. So you see where it says the domain of the log is 0 to infinity. So basically, the x values to the right side of the y-axis are accounted for. Every x to the right of the y-axis is accounted for. But you can't take the log of 0. So it's not defined at 0 or negatives. And then the range is going to be all real. So every y value is accounted for, right? So for each y, you can find a corresponding x. And then only the x's to the right of the y-axis are accounted for here, right? Okay. So then logs of 0 and negative numbers are not defined, right? That's what we just said. And here we ask to find the domain. So again, so in general, when you find a domain of a log, again, this guy here has to be strictly greater than 0. So that's all we're going to do. We're gonna set that portion strictly greater than 0. So to find that domain, we're going to say 2 minus x has to be strictly greater than 0. So then if we solve, 2 is strictly greater than x. So the x values that work here are going to be, if we do this in interval notation, here, let's look at the graph first. So here's positive x and here's 2. So if x is less than 2, are we talking about the numbers to the left of 2 or all the numbers to the right of 2? If 2 is bigger than x, are we talking about the numbers to the left or the numbers to the right? We want to keep the numbers to the left, right? Because x is smaller than 2, the alligator eats the bigger thing, so the 2 has to be bigger. And because there's no bar, we use a parentheses, right? So this is the graph of that solution. And now that you have the graph, to me, that's the easiest point to talk about interval notation. So the far left is what? Negative infinity. So the far left is negative infinity up to 2. Infinity always gets a parentheses in this context. And because there's no bar, 2 gets a parentheses. So then this is our domain. Okay. That's our domain. All right. Let's see. Let's hang out for like another 5 minutes, So I think this is, this is not obvious, a lot of these things, all right? So you're trying to take some time to kind of go through this together. And you see it here, negative infinity up to 2. Notice the use of parentheses, no brackets, okay? So there's some properties of logs. For any base that's positive where the base is not equal to 1, so log of a base a is equal to 1, right? So this is one property. Log of 1 is generally 0. The log of a base a is 1. Log of 1 is generally 0. Log base a of a to the x, basically this power comes in front. So, because again, log base a of a is 1. And because logs and exponents cancel, the x comes in front. So all you're left with is x. And again, logs and exponents are inverses of each other. So these guys cancel each other out and we're left with x. These are some main properties of logs. Okay, so let's see if we can see this in action. So I kind of went on and left the details here, but it said it asks us to sketch the graph of this log, right? So if we were going to sketch this graph, my recommendation would be to rewrite this log as an exponential. So the base would swing. So then you would have x equals 3 to the power of y. I personally would choose the values of y, find the corresponding x's. right? If you write it as an exponential, choose the values of y, then it's easy to find the corresponding x's. You get clean points, and then you just plot the x's versus the y's, right? When you plot the points, you get a shape like this. So again, this is the general shape of the log function. Notice that the domain of this, the very left to the very right, is 0 to infinity. So exponential functions have a horizontal asymptote in the form of the x-axis. When you go to look at the inverse, and when you look at the log function, when you rotate it by the diagonal y equals x, now has a vertical asymptote in the form of the y-axis, right? So with no manipulations, log functions have a vertical asymptote where it gets really, really close to the y-axis, but it actually never reaches it, without any manipulations. Okay, let's hang out for a couple more minutes. So then the first method that we use to graph the log function, we're plotting points, choosing either x or y and finding the corresponding component, plot the points. Another method is, well, it's kind of a repeat. But they rewrote the log as an exponential. They graphed actually, this is the inverse. It's not even the exponential form, but they graphed the inverse and then they rotated about the line y equals x, right? So, that's this. I mean, and it's kind of like a rehash of what we did, because when we did it, we wrote it as an exponential form and then chose the y, find the corresponding x. They went on and found the full inverse. To find the inverse, you switch the x and the y, and then you're kind of repeating some of the steps that we already did. Yeah, but it's fun as long as you have one way to go about it. So let's see, from 3.1, we have properties of exponential functions. So exponential, keep in mind, has this shape like this, where logs have a shape like this, right? The domain of exponential is all reals and the range is 0 to infinity. Because we're dealing with the inverse, that means these properties switch. So the domain of the log is 0 to infinity and the range is all reals. Exponential function have a y-intercept of 1 and no x-intercept. And then when you take a look at the inverse, the x-intercept is 1 and there's no y-intercept. For exponentials, the x-axis is a horizontal asymptote. For logs, the y-axis is a vertical asymptote. Okay, this is just kind of recapping. Exponential function is 1-to-1. That means it passes the horizontal line test, which means it has an inverse. To show algebraically that a function is 1-to-1, we show that two different y values are the same. That's true if and only if those corresponding x values are the same, right? If you start with something like this and you can't get to something like this, then it's not 1-to-1. So it's like showing uniqueness. Hopefully we can get an example where we see that in action. Also, the log function is 1-to-1, right? So it's a similar thing. You start with two different y values. You show that the x values have to be the same. The exponential function is increasing if the base is larger than 1 and decreasing if the base is between 0 and 1. And the log function is increasing if the base is larger than 1 and decreasing if the base is between 0 and 1. See, okay. Let me try to get to a few more of these properties. This is the general shape of a log where the base is larger than 1 on the left, and then where the base is between 0 and 1 on the right. Right? So this one is like the generic log shape, but then this is like where the base is between 0 and 1. Okay, so we are out of time. So if you wanted to see like the remaining presentations, you have to use my pre-recorded lectures. Okay. So, we did the best we could with the time there. We paused. Would you guys like to ask any questions? I know that was a little bit intense. So because of stuff like this is why I encourage you guys to work together. I know you do the best you can with the professor. When it's just not clicking there, then you team up with your classmates, a tutor. You keep in mind you have already paid for tutors, right? The tutoring service is included in your tuition, so you definitely want to link up with them, right? I'll do the best I can. We can do the best we can together. If you can't get it from me, get it from a quality classmate or a tutor. or Pearson. Get it from somewhere, as long as you get it, right? So you have to do your best, forget the rest, don't stress and be blessed, okay? So if there aren't any burning questions, we're going to end the session here. Let me go ahead and load a copy of this PDF for you all to access, College Algebra 2. I'm gonna send it. So when this bar finishes loading, anything that you saw me writing, you'll get a copy of it, and you'll have the rest of the instructor notes for this section, so you have all the details. Yeah, okay. So on Wednesday, what we'll probably do is take some time to go through as many homework questions from this section as we can together, okay? And on that note, if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.
I have a question for attendance and stuff.
Okay.
Like, we're able to, sorry, my name's Xavier McDaniel. Were you able to give me for attendance and stuff last week? Because I sent you an email and all that, but I haven't responded.
Did you attend, like, did you miss the class or something?
Oh, yes, I tried to get in later, but unfortunately Blackboard wasn't working, so I couldn't come in.
Yeah. I remember that. Okay. Yeah, let me update that right now. Because I meant to update it last week, and it was on the fritz for me as well. I did screenshot it. But yeah, thanks for reminding me. I know there was another student that had a question about the exam. Let me update the attendance. And what's your last name again?
McDaniel.
Yeah. Present. Okay, I have you updated. Yep.
Okay, because I was also curious about how the grading system work in terms of attendance, since because I accidentally missed that one, it went from like 100 to an 83 or so.
Don't stress too much about that. As long as you're coming on a regular basis and you're submitting your assignments, the attendance really only becomes an issue like if you acquire too many absences, and then it doesn't affect your grade, but you can be booted from the course. So it is important to kind of stay on top. If you know you miss, we need to kind of communicate, and either I might give you, just make sure to kind of stay on top of that, because you don't want to be in that boat of getting booted, but it doesn't affect your grade directly. So any kind of grade that you see for attendance is really just for record keeping. Periodic. Yeah, go ahead.
I was confused by it since there was no percentage on the syllabus and stuff. Okay, then.
Yeah, it's not a direct correlation. It's yeah.
All
okay.
Right. Thank you very much.
I know there was another student that had was trying to clarify something about the exam. Are you still there? Going once, going twice.
Hey, when is our first exam?
It was due last night.
It was last night. Okay.
But
and how long is it up for?
No. It was due last night. Like it's already. That's what was all last week. But you're not out. With all of our assignments, we get unlimited attempts. You can work on any assignment past the due date. So even though exam 1 was due last night at midnight, you can work on it and still earn up to 90%. Like if you get a perfect score, that's a 90, right? So the highest you can earn when it's late is a 90.
Okay.
Right? So, but you get unlimited attempts, and it's there. Okay.
All right. Thank you so much.
Okay, I don't know who the student was that had a question about his exam. We might have to try again another time because I think he got off the call. Okay, guys. Any other questions before I hop off? Going once, going twice. He's probably for the next class. Yeah, he's for the next class. Okay, guys. So enjoy the rest of your day. We're going to end the session here. And from one beautiful mind to another, take care. Let me check the chat. Yeah, I think I got him. Yeah.